Hello, everyone. Welcome to SAT Math Question of the Day. Oh, Seth. Okay, that's good. This is Professor Emeritus Seth Chaiken, University at Albany. Hi, Seth. Joel Chaiken, his brother. My daughter made a great suggestion. We want suggestions. She said at the beginning of the video, say that if you want to send us a question to go over, you should send it to us and we will look at it. We'll try to do it. Send us questions at SAT Math Question of the Day SAT Math Question of the Day at gmail.com. SAT Math Question of the Day. Single question. Question of the Day at gmail.com. I'll get better at that the more I say it. Okay, so here's the question. It looks like a word problem because it's got a problem. It's got words in it. Let's see. What? Yeah. Okay. I know. I mean, whatever. Okay. One end of a spring. It helps me categorize the problem.
Well, first it gives an equation. Starts with an equation.
Yeah, it starts with an equation, right. One end of a spring is attached to this. The equation is generally the rule. So right now, in this question, we focus on the rule. It's the only thing.
No, let's read the question.
Okay, fine. I'll stop on screen. One end of a spring is attached to a ceiling. When the object of a mass m is attached to the other end of the spring stretches to a length of L centimeters, as shown in the above equation. What is m when L is 73?
Okay. Well, I think it's helpful to note that this is really an algebra problem.
Yep.
When L is 73, they want you to solve for m.
Yep.
That's all it is.
That's all it is.
And so it's helpful to take your pencil and write the 73 up here, cross out the L, and look at it, and your goal is to solve for m.
Yep.
Now, a cool approach is as follows. Look at the answers.
No, it's pretty. Yeah, that's
right.
Really good. Yeah.
73 and 279 are much too large to be possible values of m because the left-hand side is 73.
Right.
Positive 24 is added to it.
Good idea.
So m can't be that big.
Right.
Well, what if could m be 27 or so? Well, about 30. Well, let's say it's around 30. You'll get 90 already. Over 90.
Got it.
That's no good. So the answer must be 14. Bingo. You move on to the next question.
That is a great way to do it. Unfortunately, I'm still sort of stuck in.
However, what we could do is review the conventional way. Solve the equation by means of simplifying while preserving the truth of the equation until you get an equivalent equation that has the form m equals the answer.
In this case,
do you want to do that for us?
Actually, in this case, you could take the compromise approach, which probably would have been the way I would have done it. It wouldn't necessarily have occurred to me to look at the answers so that way because, frankly, this is a pretty easy question. So I probably would have done this. Plus 3.5m. I would have subtracted 24. Oh, this is horrible. You have to do carry.
Yeah, this is horrible.
Oh, that is nasty. They purposely did that.
Yeah,
oh, my God. Yeah. So you know what I would have done here? Maybe I would have said this is about 50. Maybe I would have said this is about... Now, the thing is, see, I didn't do it cold. Seth did it, so I followed him.
Yeah,
maybe
there you go.
Maybe I would have said this is about 50, and this is 3.5m, and then I would have done what Seth did.
So it's less than a third of 50.
Yeah.
M is less than, like 1/3 of 50 is a bit under 20, right?
Yeah.
Yeah. How much is? I don't even care. A third of 50. I don't even know.
No, it doesn't matter. All your stuff
but
matter.
it's a third of 50 is less than half of 50, so it's less than 25.
Who cares?
So the answer has to be less than 25.
Yeah.
And it's so it has to be 14 because it's a multiple choice.
Right. So, but probably this again. I didn't do this cold, right?
Yeah.
If I saw this, I would have said I'm not going to waste my time carrying.
Oh,
The other thing
okay.
to notice is that all of these answers are very far apart.
Yeah.
When these answers are far apart, then you have justification to approximate this to be 50. If these answers were close, like 14 and 14 and a half, forget it. You couldn't just, but so that's why, again, parallel
like suppose they gave you choices like 13, 14, 15, and 16.
Then you couldn't make this approximation that I did.
Yeah, right.
And then right here you would see that, the only answer is this.
Yeah,
so
this sure this leads me to think that the SAT was designed so that designed to reward students who could quickly resolve questions that look like they take a lot of work, so that they could gather time to spend on the really hardest questions.
Right. And I keep saying from the very beginning, pattern.
Yeah.
You look.
So again, this is a case. You may have heard me lambast the notion of the word pattern. This is a case where it is a pattern.
Ooh, thank you.
It gives you the equation. Yes, the pattern is an equation is given. One of the letters in the equation is a parameter, which means that a value is given right to you. There's another letter that functions as a variable, and the pattern is take an equation, substitute a letter for a number, and then solve for the other letter.
Right. Although in this case, I actually would say it's more of a. We're using the word pattern in different ways, but it doesn't matter.
Yeah.
And then,
should we say a little bit about the physics?
No, we should not say a little bit about. First, I want to say one thing. We could say a little bit about physics, but we'll release everyone to go on their merry way. I just want to say one really quick thing. When in 8th grade, when kids start starting in 8th grade, this is what I call the backwards problem, because you're given the answer and you have to back solve to get the number that gives you the answer. When you start out, when you're learning algebra, usually they'll write an equation, the answer y is equal to 3x plus 4, and they'll say when x is 3, what is y? This is the backwards question. Here they're giving you the y is 12, and then you have to back solve to get 4. I assume that by the time you're taking the SAT, you can distinguish and you're not too intimidated by what I would call the backwards question, which is where you're given the final answer and you have to back solve to get the...
Well, you just have to keep your wits about you about which way you're going.
See, what's nice is that if you don't want to think too much, which in algebra sometimes you don't want to think, you literally just put the numbers in and you let the algebra do the thinking. Do you sort of agree that algebra is useful because algebra can do a lot of thinking for you?
Yes.
Good. We agree.
Oh, yeah, definitely.
We agree on something. I like that. We're starting the week off well. Okay, so let's release everyone. And sure, if you want to talk about the physics, we can talk about the physics. This is a y equals mx plus b problem, isn't it?
It's a what?
This is a y equals mx plus b problem. You start off at 24, and it's. But we could talk about that.
No.
Okay, wait. Let's release everyone. So they can go on their way.
Release
the masses. Okay, everyone. Thank you for watching this. We really appreciate it. Like us, dislike us, give us comments. All the comments we need because we want to make this stuff really for you. And now we are going to talk. Seth made a recommendation to talk about the physics. I said this is y equals mx plus b. Let's go. Take care, everyone. Have a good day, and feel free to hang on.
Yeah.
Go ahead. All right.
Well, in this case, it's a y equals b plus mx.
Oh, come on.
And the m is x.
Yeah.
Right. So.
So what's the difference? Addition is commutative.
Well, the letters. You have to watch out about being confused by stereotype choices of letters.
Okay.
Like the stereotype choice of a letter for the slope is m. But in this problem, the slope is 3.5.
Right.
The stereotyped x-axis variable is x.
Do you think
In
they
this
did that on
problem,
purpose? Do you think
that
they did that on,
variable is m.
Do you think they did that on purpose?
I don't think so.
Okay.
I think what they did on purpose was presented a topic from physics.
No, but see, look, and
And they did was present a law of physics, and they used the letters to indicate quantities in physics.
Right.
In the case here, M for mass,
Right.
and L for length.
Right. Okay. Yeah. Yeah. It makes sense.
Yeah.
So anyway, what's the physics?
Well, the physics is
Seth got his undergraduate degree in physics, so he's a physics guy.
So the physics, I'll do physics in blue.
Good idea.
The physics is, we have a rigid support. We have a so-called ideal spring, and ignoring the weight of the spring has an unstretched length. What units do they use?
They're
kilograms and centimeters. 24 when there's nothing pulling on the string, the length is 24.
Right.
And then if you you attach a mass to it, and then if you attach a mass to it, it stretches the spring down.
Right.
It stretches the spring down. You attach a mass with a mass with mass m, it stretches the string down, and the law says that let's say I'm measuring the length to the end of the spring, not the ends of the weight. What happens is the length becomes 24 plus 3.5 times m is this distance from here to here. Okay, so the amount of additional distance called delta L equals 3.5, and I'll put in the units now, 3.5 centimeters per kg.
I'm moving the screen, Seth. I'm moving the screen. So
times the mass in kgs. Okay.
Right. So,
well, what they teach in careful physics courses is that this situation will fail on the moon, because when you go to the moon, the spring constant and the mass are unchanged. What changes on the moon is how much force gravity pulls upon a mass. Right? On Earth. Oh, I don't know. What's it converts between newtons and pounds. Was it 32?
Yeah, 32 feet per second
32
feet per second per second.
Yeah. So that's the
acceleration of gravity.
No. It's using metric.
Newtons per 9.8.
Newtons per kilogram.
Oh.
Yeah. Is 10 meters per second squared.
Right.
Is an acceleration of gravity.
Yeah, 9.8.
Yeah. Meters per second squared. So you multiply this by mass in kilograms.
Yeah. So now this has nothing to do
and
with
we get the force in newtons.
Right. Wait, but
using F equals M.
But to get back to more, forgetting out the physics right now.
The physics of it is that a so-called ideal spring, how much it stretches, the difference in length is proportional to how much force you're pulling on it.
Right. And then there's something called the spring constant, which is
that's called the spring constant. It's called Hooke's law.
Right.
Now, if you want to play with it, well, if you play with it, you'll get in trouble if you use a rubber band. Because if you stretch a rubber band long enough, it starts to pull with a lot more than proportional to the force. It kind of gets rigid, and then if you pull it really, really hard, it doesn't stretch much, and then it breaks.
Yeah. Well, like all things in physics, things only work under certain circumstances. You can't expect the laws of physics to work.
Yeah. So this kind of spring that obeys this law of force and stretchiness and stretched amount, that kind of string is called a linear string, a linear spring.
Right. Good. Yeah. Now, Seth, you said something about the moon. On the moon? Isn't the force that it takes to pull a string still proportional to the length? Yeah, but that's not what you said. You said on the moon it doesn't hold.
Yeah. No. The force, when you measure the force using a unit really of force, like a Newton.
Okay.
But here, they specify now physics. When the thing is in physics, mass roughly means how much stuff there is. Right? And then gravity acts on mass by causing a force to appear to be pulling on the mass. Right? That's proportional to the amount of mass.
Right.
And how much force that is, the constant of proportionality depends on the strength of gravity.
Right. Exactly. So
and the strength of gravity and the way what's cool about gravity is that the strength of gravity has the property that it will accelerate an object at an acceleration rate that is independent of the mass of the object. Right. And so the strength of gravity can be specified by the acceleration, that is the amount the speed increases per second. In other words, the units are distance per second.
Right. Yeah.
When the object is acted upon by gravity alone.
Yeah.
Yeah.
The bottom line is a brick would appear to be lighter on the moon than in
so would a feather
on Earth. What?
Yeah. So the thing is that what we distinguish, physicists are very careful to distinguish between weight and mass.
Right.
Weight is the amount of force that gravity applies to an object. That's the weight of an object, and it depends on where in the universe you are.
Right.
The mass of an object gives the amount of stuff in the object, and that is independent of where you are.
Right. Okay. It's a good little physics lesson. Very confusing though. When you first learn this stuff, it is confusing. Okay. That's it.
Okay, that's all, folks.
That's it. Okay, that's all, folks. Literally, to quote Bugs Bunny, that's all. Okay, everyone, have a great day. We already said goodbye to everyone, so we're just going to leave. Have a great day. Bye-bye. Thanks for the physics lesson, Seth. That was good.
You're welcome.
Good. See you later.